Swayam Prabha. Digital India. Educated India.
Welcome to module 36 of NPTEL NOC, an introductory course on point-set topology. So we begin a new chapter today, an introduction to dimension theory. So dimension theory has several approaches. Amongst all these available versions, we will choose one such. Of course, they are all topological dimension theories. Our aim here is reasonably modest one. The depth and width of the subject does not allow us to do much in an elementary course like this. We shall discuss the zero-dimensional case thoroughly and then take you to the doorsteps of higher dimensions. Our final goal will be to prove that the Euclidean space Rn is exactly of dimension n. If you are interested in more details for a comprehensive study, you are welcome to read this book of Hurwitz and Wallman for this particular dimension theory. So module 36, the title is separation of sets. It has something to do with the separation axioms that we have studied so thoroughly, and it has something to do with connectivity, right? But this is nothing to do with the separability of a metric space, or separability of a space as such. So there are too many different ways the word separation and or its modifications are used. So you have to be a bit careful here. Somewhat unexpectedly, we are beginning with something to do with the connectivity. We have seen how connectivity crops up from the concept of continuum in the construction of real numbers. The space of real numbers is taken to be of mathematical dimension 1. Why I am saying this one is, whether it is topological dimension or a vector space dimension and so on, various dimension, all of them you can call them mathematical dimension. That dimension is 1. The word dimension in physics has slightly different connotation. So in all mathematical dimension, the space of real numbers must be having dimension 1. So we begin our study at one stage before that, namely understanding zero-dimensional spaces. For example, if you are studying a linear algebra vector space, the zero-dimensional space is just a zero vector space. There is nothing more than that. So that simplicity makes the life very easy with linear algebra. But that is not the case in topology. So we are going to spend considerable amount of time in studying zero-dimensional space itself. One of the peculiarity of connectedness concept is that the definition is in the negation. In fact, we define disconnected space, and then if the space is not disconnected, then we say it is connected. So we would like to come to the opposite of this property, namely disconnectivity. Okay, so we are going to discuss certain stronger forms of negation of connectivity, namely disconnectivity, which may be termed as stronger forms of separation axioms, namely Frechet space, T0, T1 space, T2 space, T3 space, and so on, regularity, normality, and so on. Okay, so all those things will come into picture now, ala indirectly. So let us begin with a definition here. Given any two disjoint subsets A and B in a topological space, we say they are separated if there exists disjoint open sets U and V such that X is the union of U and V. Both U and V are disjoint, right? So that is why I have written the SQ cup here. A is contained inside U and B is contained inside V. After that, you can assume both of them are open, U and V are open, or U and V are closed. It is the same thing. So the term here I am going to use is that A and B are separated, okay, subsets of X. Of course, to be separated, first of all, they have to be disjoint. People also use the word disconnected, for this one, but that is too somewhat confusing for me, so I don't want to use that terminology here. Okay, such a writing U and V like this is called a disconnection. Okay, so what we will call this as separation. So we had such a notation already introduced also. So we are just writing it as X equal to U vertical bar V. You remember that. So that notation also I may use sometimes. In any case, starting with disjoint closed subsets, we have enclosed them in U and V. The only thing is, totality of U and V is the whole space X is the extra thing. Otherwise, this is just like normality, right? So you are reminded of normality. Okay, so what here is a stronger thing. Namely, in normality, the union of two open sets you get is not the whole space. They are disjoint, fine. But here it is the whole space that makes both of them closed also. Okay, so this is going to be quite a strong condition. No doubt it implies normality as soon as there are disjoint non-empty closed sets in a space X. This property implies that the space is disconnected. So even that is true. Whereas there are plenty of normal spaces which are connected, right? Whereas if you have this property, okay, disconnectivity for every disjoint closed sets, okay, then the space will have to be disconnected. So this is very strong. Hausdorffness, regularity, normality, etc. can be termed as local properties, whereas the one which we have introduced now is a global property. Okay, so let us consider the following conditions on a topological space. To make sense out of these things, you should have the topological space as at least 2 points. The singleton set, singleton topology is both connected and it will satisfy these properties also. So don't get confused with that. At least you assume that there are at least 2 points in the space. Then consider these 4 different axioms of disconnectedness. Okay, axioms of separation. Whatever word you want to use, there is going to be some confusion. Okay, so I can call it the axioms of separation because I have introduced a notation S0, S1, S2 and S3 just to include people who are using this kind of terminology. I have put that as a title also, that's all. So S0 just says connected components of X are all singletons. Any two distinct singletons in X are separated is S1. Any closed subset A is separated from any point outside A. Any two disjoint closed subsets in X are separated. Okay. So S0, S1, S2, S3, you can see that these three things are one stronger than the other. But this S0 seems to be not in this list. Why should it? This is odd man out. It looks like it, but this is the one which connects the connectivity with these properties. In this section, we shall do a comparative study of these conditions, the four conditions above, okay, and indicate their importance. Note that S0 is somewhat different from other three statements. Let us give it a more descriptive name. Sometimes I will use that, but for safety I will use it as S0 only. Okay. So any space which satisfies S0 will be called totally disconnected. Okay. I want to caution you that different authors may use same terminology to mean different things. So their total disconnectedness may be different. For example, one of the books which I am very much using and respect, I have a lot of respect for this one, is Simmons' book on modern analysis and topology and modern analysis. Okay, in this book, a space satisfying our condition Si is called totally disconnected. S1 is called totally disconnected, not S0. Okay. We shall see that property S0 relates the connectivity to the other three axioms of separability here. All right. So let's go ahead. S0 is seen to be hereditary. If something is totally disconnected, namely all the singletons are the components, then for any subspace the singletons will be component. So it's hereditary. It can be seen without much difficulty that S1 and S2 are also hereditary. Okay. S1 is hereditary is just like Hausdorffness being hereditary. S2 is hereditary is just like regularity is hereditary. When you come to S3, it is similar to normality. Just the way normality fails to be hereditary, this will also fail to be hereditary. Exactly same reason. Okay. But it is weakly hereditary in the sense that closed subspace of a S3 space will be S3. Okay. Starting with a closed subspace and then taking closed subsets inside that, they will be closed in the original space also. Then if you take a separation in the original space, then you can restrict it to the subspace, then you are done. So that is the proof that it is weakly hereditary. Okay. Now S1 implies S0. What is S1? Any two distinct points, there is a separation. Okay. If there is a separation, they can't be in the same component. So if any two points cannot be in the same component, all the connected components are singleton. That's all. Okay. It is quite often people confuse S0 with S1. So caution, S0 does not imply S1. We will see some examples soon. Okay. Unfortunately, the word totally disconnected is used for this one also. So that for some authors. So you have to be careful with that. Alright. Let us go ahead. If x satisfies S2, then every point in X has a neighborhood system consisting of open as well as closed sets. Those things are called clopin sets. And conversely, so this could have been taken as a definition of S2. Why? Take a point, take a closed set away from that, or take a closed set and take a point outside that, which is the same thing as taking an open set and taking a point inside that. Then what do you get? You have a closed, open and closed subset, clopin sets, right? That clopin set means what? Open and closed. You take the complement, that will be separation. Okay, so both ways, I mean, this argument can be seen both ways. So S2, if and only if every point of X has a base, local base consisting of clopin sets. S0, S1 and S2 are all productive also. Once again, the proof is similar to proving that Hausdorffness and what is the other one? Regularity are productive in these two cases. This case is just like proving product of connected spaces is connected. It's much simpler than this one. Product of disconnected space, totally disconnected space is totally disconnected. It's like that's what you have to prove. Okay, so it is similar, but let us just have a look at the first one. Why S0 is productive? Okay, suppose each xi is a family of xi is a family of spaces which satisfy S0. Now I am taking A is a subset of product space and A is connected. Okay, actually I am making connected component with more than one point. Then I should get a contradiction. Alright. A is a subset which connected component has more than one point. It actually just a connected set with more than one point give you a contradiction, that's all. Then there exists xy in A and an index I such that xi is not equal to yi because they are different. At least one coordinate must be different. But then if you look at the projection of A on ith coordinate pi I of A, this will be a connected subset because it's an image of a connected set under a continuous function, right? So it's a connected subset of xi with more than one point because xi is not equal to yi, right? That's a contradiction because we have assumed that connected components of xi are singleton. Therefore, the product satisfies S0. The converse, why the converse is true? Suppose the product satisfies S0, but then each coordinate space can be thought of as a subspace of the product space, right? So this argument we have used several times. x1 cross x2, if you look at x1 cross one point will be a subspace of x cross y, x1 cross x2, but it is homeomorphic to x1. So as a subspace, because it is hereditary, it will be S0. So each coordinate space is S0, which same thing as each xi is S0. Okay. So I will leave the other things here, namely productivity of S1 and S2 as a entertaining exercise to you. Okay. You should do at least that much so that you will be familiar with this concept. Okay. The earlier you do them, the better. So before reading the next, before coming to the next module, try to do this exercise so that you will be completely familiar, completely thorough with the definition at least. In the most general situation, none of these conditions imply any other. Though I said this looks like stronger, stronger, stronger. Okay? So let us see why they are stronger, in what sense they are stronger. Under additional conditions, there will be implications one way or the other. This is what we concentrate upon for some time. When S0 implies S2, implies S3, etc., other way around and so on. This is what we are going to do. Just like the usual separation axioms, Hausdorffness, regularity, normality, etc., the first key is the freshness. If you admit that all the spaces are T1 spaces, then automatically S3 will imply S2 will imply S1 implies S0. Okay. Exactly same reason as T4 implies T3 implies T2 implies T1. Exactly same way. First you have to assume that it is T1. Otherwise, just normality does not imply regularity. Same way, S3 may not imply S2. As soon as points are closed, S3 will imply S2 because in S2 I have to take only a closed set and a point. Okay, disjoint closed set and a point outside. They will be disjoint closed subsets, so you can apply S3 and come back to S2. Similarly, in S1 I have to take two distinct elements, but they can be treated as disjoint closed sets. And I have already seen that S1 implies S0, right? Why? Because any two points are disconnected here. There is a separation, means they are not in the same connected component. So this part is easier without the T1 axiom also. This part we have already seen. So under T1 they are like this. So from now onwards we shall always assume that our space is T1 space. Then we will try to see whether we can come back. Okay, and that is where we have to put more and more conditions. Next, note that each of S0, S1, S2 and S3 respectively is strong form of freshness, Hausdorffness, regularity and normality respectively. Any connected metric space with more than one point. By the way, why S0 implies freshness? Tell me. I say it is stronger than that. Connected components are singletons. Singletons are connected components. Connected components are always closed. Therefore, singletons are closed. Okay. Any metric space with more than one point will serve as an example which is actually T5 space, right? But does not satisfy any of the S0, S1, S2 and S3. Only thing you have to put is connectivity. Okay, none of the spaces S0, S1, S2, S3 are connected spaces. Oh, that is the meaning of why this S0 is it brings the connection between connectivity and separation. Okay. So before proceeding further, we shall examine some examples now. It turns out that all these examples are separable metric spaces. and satisfy S2. Why I am doing this one? Because finally we are interested in dimension theory developed by Wallman and Horowitz, right? So there the separability means there is a countable dense subset. Separable metric space is a blanket assumption. Okay. So let us examine these examples. They are somewhat out of your way so far. Any countable metric space satisfies S2 for given any point x and a neighborhood of x. Choose R positive such that BR of x is inside U. Now let x1, x2, xn be an enumeration of points of BR of x other than x itself, because BR of x is countable. It's a countable. A whole metric space is countable, right? So I am just writing down, labeling all the other elements. They may be finite, they may be infinite, doesn't matter. The dot dot dot. I am not saying that it is infinite. It is countable, that's all. Choose a real number R prime such that 0 less than R prime less than R, and such that R prime is not the value dxxi. So dxxi as I ranges over 1, 2, 3 and n and so on will give you only countable number of real numbers. Okay, between 0 and R there are uncountably many, so I choose one R prime which is not equal to any of them. It follows that the open ball of radius R prime around x is contained inside U because R prime is less than R, but boundary of R prime x wherein equality occurs, that is empty, because equality occurs, they are distinct from all these xi's, you see, that's why. The boundary is empty. Whenever you have an open set which boundary is empty, it is a closed set also. Okay, therefore x is BR prime x union, the complement is also open, is a disjoint union, x is here, right, and this BR of x prime is contained inside you. So you have got a clopin subset. Okay, so what we have shown is every point has a neighborhood system consisting of clopin subset. So that is the S2 that we have seen earlier. Any subspace of R which does not contain any open interval satisfies S2. Like we have been studying all these examples quite some time. Q, R minus Q, that's irrationals, Cantor set, these are all examples of S2. Okay, namely for each point you can find a neighborhood such as the boundary of the neighborhood is empty. That is the nice way of remembering this S2. The subspace Q power n of all points in Rn, all of whose coordinates are rational. Okay, Q is contained inside R, you take Q power n contained inside R power n. That also satisfies S2. All that I have to do is, given a point, use coordinate rectangular boxes, okay, with one of the coordinate irrational. Then the entire box will not be inside Q. So boundary of this entire box, open box, will be empty as far as Qn is concerned. So similarly, the subspace I power n of Rn of all points whose coordinates are irrational, the other way around. Okay. Other way, this is not complement, by the way. Here all points are rational, here all points are irrational. So that also argument is same thing. Okay. So this also satisfies us.
Yes, sir. So from 2, Q and equation are S2, therefore product also will be automatically S2 also, one way of looking also.
Yeah, yeah, you can use that here because S2 is productive, right? So you can use that one also, no problem. Moreover, now comes, you see, now I am mixing up. For this you will have to use arguments, down to this way, not products. The subspace R2, 1, 2 up, 1 I have used here, R2, 1 of all points in R2. So that upper subscript corresponds to the where we are taking, but the lower subscript, exactly one of whose coordinate is irrational. Okay, x comma y you look at, either x is rational or y is rational. If both are irrational or both are rational, I am not taking them. Okay, so this space is also S2. So to see this one, you can't use products and so on. This is not a product space now. So you have to directly say that for each point you must be able to get a neighborhood such that the boundary of the neighborhood is empty. Okay, an open subset, so the boundary of that is empty. That's what you have to do. So how do you do that? Each point of this space can be enclosed in an arbitrary small rectangle whose vertices are rational. Okay, if the vertices are rational, they are not inside R21. Remember that. Only one of them must be rational, right? Therefore, if the vertices are not inside this one now, and then what are the sides? The sides have slopes plus minus pi by 4. So they are not coordinate lines now. Okay, so slides plus minus pi by 4, which just means that they are points x comma x comma x, or x comma minus x, or minus x comma x of that nature, right? Or x comma plus something, and plus something means what? That plus comes from one of the coordinates of these end points, the vertices, but that is all rational. So if x comma y, the difference will be what? Difference will be again rational. So both of them cannot be rational. So slope plus minus pi by 4 means that. Okay, so the boundary, this boundary of this rectangle is not a point, is not contained. No point of that one is contained inside R2 one intersection, that is empty. So therefore this is S2. This satisfies S2. You try to do that inside R3, then you will have a lot of problems. Even this argument won't work. This lines with the slope plus minus pi seems to work only for only for r equal to 2 now, n equal to 2. But we have other ways of dealing with it here. Start with two indices m and n, m less than or equal to n, that's all. Okay, some numbers. Again similar notation. Rnm denote the subspace of points inside Rn. Exactly m of the coordinates are rational. The same construction, this 2 is replaced by n and 1 is replaced by m. Okay, this space is a generalization of the above example. However, the proof of this, that it satisfies S2, is not straightforward. At least the method that we did in 4 doesn't work. Try it. Of course you have to wait, and then after some stage I will give you the proof. Okay, so that is bit involved proof here. Just take R3 here. Okay, instead of 4, instead of 2, then you can take any m. Then the problem will be there.
Can n equal to n also here?
N equal to n, I think we have already considered this one. You see, that will fall inside this example, Qn, right? Yeah, here, Qn. You see, Rn, if you take all the coordinates are rational, it is Qn. So that is already, so it's a special case, right? So the problem is only when it is smaller, then you have problem. Also when n is bigger than 2. So bigger, for n equal to 2 we have already done it. Okay. So I think today this is enough. So next time we will continue with more examples. Okay, so that we are thorough with these concepts S0, S1, S2. So thank you. That's all today.